Hi everyone, welcome back to another episode of the Rocket Media. Today I am with one of the most extraordinary mind in physics. He held the IIT rank 1 in 1987. He did his PhD under Nobel laureate David Gross and his postdoc from Harvard, after which he returned to India and joined HRI, and now he's currently serving as director of ICTS. I am talking about none other than Professor Rajesh Gopakumar. So, hi sir, how are you?
I'm good. Good to be talking to you again.
So I have interacted with him before, and this is his second time on my channel. And today we're trying to bring something different, and I hope you are ready for that too.
Yeah.
So
let's go.
first, I understand this place, ICTS. So I spent some 4 or 5 days here, and I found this incredibly different. I have never seen an institute like this before in terms of its philosophy, design, and environment. So if you could just explain me the culture and ICTS.
Yeah. No, this is what we are aiming to create an institution where, which is different and different in the way that it for people who are here, our students, our faculty, our visitors, they feel a certain energy. They get a kind of the buildings, the architecture, everything we hope will give them a sense of energy to be more creative in their science, to think big thoughts, big ambitious thoughts, come up with some breakthrough ideas, and feel a certain buzz in the air, so that, that's what makes your mind race and your heart race fast. You feel you're in the midst of great ideas. You feel you can also contribute. If you look at all the blackboards in our campus, there are always some students, bunches of people around these blackboards, very animatedly discussing ideas. So that's what I feel measures the health of an institution. And from whether you're a PhD student or a visitor or maybe some undergraduate students, you should all be participating in this big culture of science, of doing science. And so that's one of the ideas. And we act as a national facility. So it is not unlike many institutions which are mainly for their own faculty, their own students, etc. Here we are very open to the world. So we have continuously programs, workshops, meetings, schools, different kinds of activities happening 51 out of 52 weeks in a year. And at any given time, there are 80 to 100 participants in ICTS from outside our institute. And these are half of them are PhD students or master's students, sometimes undergraduate students from different universities, in IITs, ICERs, so many institutions across the country. And then about 20-25% are people from outside the country, so that these young people from various institutions also get to interact with some of the best experts from around the world and develop a certain enthusiasm for the subject that they are working in, because often in India, many areas, we have only a few people in a given institute. But here, by bringing people together, that aggregation helps in new collaborations, in new ideas, and training our young students. So in that sense, we see ourselves as a facility for the whole community. So that way we are very welcoming, and we try to be, I think, welcoming and open to everyone, and so that everyone can participate in this activity.
Yeah, right. I think this is the kind ki great science is being done. And talking about the the core design of the institute, I think it somehow promotes conversation and discussions. So the areas that I have seen, be it a cafeteria, be it blackboards, and even a mess, inside of the cafeteria we have these tables in nature, and
Yeah.
I saw a couple of students just solving random problems on the blackboards, and
Yeah.
when you wrote an article about blackboards are meditation. So if you could tell us about this conversation and collaboration thing at ICTS.
Yeah, so I'm very grateful to the architects who actually built this campus together with the founding director, Spenta Wadia. I think they came up with this wonderful design, which is very appropriate for the climate in Bangalore also. We are here sitting in June and it is so pleasant outdoors. And much of the year it is like that. And so these spaces that are there in our campus allow people, like you said, to come together. And when they come together over chai, coffee, meals, they start talking, and there is a culture of not just, I mean, okay, gupshup also happens, and it is also natural, but also science gupshup also happens. You exchange ideas, so that there is a culture of promoting that. And these blackboards, I think, are very important because this is a theoretical sciences institute. We don't have experimental work, so blackboards, as I wrote in my essay, is a way in which you transfer the thoughts from your head to something concrete. This is the first way in which ideas are born. I mean, they are born in the head, but then that's like their incubation, and then they're really born into the world when they come onto the blackboards. You discuss with people, it gets shaped, and that's how, I mean, I think in the theoretical sciences, whether it's physics, mathematics, biology, whatever theoretical subjects that people discuss, the ideas are not always correct when they are born. You have to kind of shape them, and the shaping happens in an interactive way, and it draws in other people also. So because many of the blackboards are in public spaces, people, others who are passing by may also get interested, and they may also start contributing. So that is what we try to promote.
Yeah, or just capture ideas. So I have seen blackboards in guest house, in sports complex, even in cafeteria.
Yeah.
So every place, has those blackboards. So
Yeah.
it's really great. So, mostly people think, a great campus is about infrastructure, a faculty, or a different thing. But since you mentioned culture, so if a young researcher or anyone who is interested in physics or theoretical sciences who comes to ICTS, so what kind of a culture you want him to experience? What kind of things he can expect at ICTS?
Yeah, him or her.
Him or her,
She.
sorry.
In fact, we would like a lot of diverse set of people, and we would like them to participate in an adventure. I mean, science is like an adventure for a lifetime. It's that, and like any adventure, it is full of dangers. There are difficult times and everything. But you're participating with you feel you belong to a group of people all together, like you're going on a hike or something. When you go on a hike by yourself, it is different from when you're going in a group. So we want people to feel that here they are part of a larger adventure. They are in groups. They're all exploring new frontiers of science. So it's like an exploration. And I would like the students to get that feeling. And many times the curiosity that is there inside students, sometimes our educational system crushes that curiosity, to be frank. And I hope if that is the case, it can be brought alive again by coming to a place like ICTS. That inner child in everyone who asks questions about things they see or they don't understand, who is free to question and to kind of so we have the philosophy that no stupid questions, are only stupid answers. One of my teachers actually used to say. The questioning is good. And I think the more you question, the more you learn, the more you kind of ask sometimes new questions that no one has asked before. So that feeling I would like our students, whether they are our regular PhD students or visiting students, all of them to feel that sense and maybe take it back to their institutions also. Yes, so resources are important. All these other things are important, but the culture is what, in a sense, makes an institution more than the sum of its parts, more than the sum of their individuals.
Yeah, since you mentioned the culture of curiosity and asking questions, so My background is economics, and I researched about this interview and physics just few hours or few days, but I'm sitting in front of someone who has spent decades in this field. So definitely I thought, okay, I'll ask questions. So I thought, okay, maybe I'll ask some stupid questions, but
There are no
I'm here.
stupid questions, so you shouldn't feel
Right.
intimidated by that.
So I have seen many institutes, and I have been to many institutes, and many institutes often become bureaucratic in nature, or as you said, science should be fun and science should be adventurous, right? And I have seen in ICTS, professors are eating in the same mess, and professors are having discussion with the students. It's a small institute. So how do you preserve that inner child of students here?
Yeah, no, I mean, it is, of course, up to everyone to preserve that, but we try to at least make it so that it is not crushed by bureaucracy or hierarchy or other things like that, which is what often kind of dampens the enthusiasm of young people, because young people have much more energy than old people, I would say.
Right.
But that enthusiasm should be channeled, and if they find that okay, nothing really is dampening that enthusiasm, then I think they can flower into creative researchers, I think. And so we try to minimize that. Of course, any institution, by virtue of being an institution, has functions under certain constraints and under this thing. But within all that, we try to shield younger people from as much bureaucracy as possible. We have a great staff. I think people often underestimate the value of very good administrative and support staff, because if you have a dedicated team of administrators, they simplify the life, the bureaucratic essentials so much. And if they have a helpful attitude, if they also feel that they are also participating in this adventure, they are also not maybe scientists themselves, but they are also participants in making the institution important. And we try to give that sense of feeling for our staff. We try. I mean, there are always issues to overcome, but I think by and large, our administrative staff are so dedicated and sincere. They work on weekends, after hours, they're answering emails from visitors. All our program visitors describe that the staff have gone so much out of their way to help them when they come here, when they are visitors here. So that is also something to be preserved. It doesn't happen naturally. Many places I have seen the administrative staff are very disgruntled. They are kind of they're obstructive and so on. They kind of feel they are not really part of it, or they're treated as second-class
Right.
citizens. So we try not to have that feeling here. And so it's important, I think, to create that. That helps in makes it easier. It liberates the scientists.
Yeah, I think great institutions require everyone needs to be respected. Every idea needs to be respected,
Yeah.
and it should foster collaboration. So Indians are famous for working in silos, and now I'm seeing some collaboration here. So if you can tell us something about that, new departments are being established, and now people are collaborating with each other in terms of authorship or in terms of regular tasks and all.
Yeah, no, it's a good point, actually. I was actually I hadn't realized this in some ways, and I didn't realize how rare it is in India. But it is one of the things at ICTS in terms of the academics is that our research faculty, they are not in departments. We have only small groups, and that is also just for some cohesion. It's not an administrative structure. So they have different groups, but we don't even have physics faculty, maths faculty as separate departments or anything. They all have offices the same place, and the nice thing is, because they all go for lunch together, they are in the pantry together, their offices are next to each other. They started new conversations between mathematicians and physicists, between statistical physics people and fluid dynamics people, between biophysics people and condensed matter physics people. So all these new conversations just started organically. We didn't tell them, oh, you people should collaborate with each other or anything. We don't do that kind of top-down management. We let people explore, and they kind of, because they're talking to each other and they exchange ideas, they started these new collaborations. So some of the people studying climate sciences, some of them have engineering background, some have mathematics background, others have computer science background. So they all just start working together. In fact, the publications, there are some very good publications have come about because of this different people bringing their different expertises together for attacking a new problem. And there are some very complex problems that require large collaboration. Individuals cannot do it. No individual will have the expertise to attack all of these directions. Like climate science is a very challenging issue which needs people from a variety of backgrounds. So I'm glad that is beginning to happen here. I mean, it has been happening for actually many years now, and it is growing. And so that's something I'm happy, and I would like to foster that collaboration. And people outside have remarked to me that it is quite unusual to find young faculty across different areas collaborating. Normally there is a feeling of competition. Oh, if I collaborate, then how will it affect my promotion and this and that. I think here we have been supporting everyone, so they don't feel that it's a zero-sum game, which is what often I think prevents this kind of collaboration.
Yeah, and also I think, like, since you mentioned about competitiveness, I think Indian minds are wired, like, in a competitive nature from since childhood. So to give out exams and lot of stuff which needs to be changed. Like, we need curious minds more.
Yeah.
So I have a very nuanced question. Like, are scientists born, or are scientists are trained? Like, if you talk about IQ and those natural instincts, so scientists are born or they are trained?
It's I think there is a large amount of, I mean, this nature versus nurture debate. I think nurture plays a big role. I think there may be some aspects which are sort of maybe some traits, but in the long run, to be a good scientist, I think the traits that really are needed are ones which are nurtured, are kind of cultivated systematically. I mean, we often underestimate the power of just systematically building something up gradually, but when you do something systematically for 20 years, then you build up a certain expertise, a capability, and a depth of understanding. So, but it's a question of keeping at it steadily over time. So you have to, I like to say science is like a marathon doing research, and it's not a 100-meter sprint like the JEE or something like that, which by the way, I don't think is a very good measure of anything really, especially more and more so. And I think we are, as a nation, we have gotten too much into this thing because everything is measured by whether you've done well, whether you get through the JEE, or whether you get through NEET, or whether you get through this thing. Everything is focused on a few exams, and the children get really curiosity that we talked about earlier gets kind of killed at some point, I would say, especially through coaching classes and other such things. And so and then people have this wrong image that you're kind of, it's just something you're born with, and but you don't realize that if you had spent those years maybe nurturing your curiosity, in the long run, you would have maybe become a more creative person. So that's one thing I feel we, as a society, we should appreciate more. That nurture is very important, and it can be nurtured in school, at home, if you let people develop their curiosity and their but encourage them to work hard, but not just for the goal of doing well at exams.
So, just a curious question. So, have you met someone who had not performed well early on in school or at a primary education, but eventually turned out to be a great scientist?
Yeah, there are many such cases where people, have, for whatever reason, the education system, they didn't find it so conducive for their thinking, and they might have been very independent-minded, and so I know some very good physicists, even in India, who went to some very ordinary colleges, but slowly over time they developed into extremely talented, very creative physicists. So that is the case. It's not that you have to go to this college, that university, that this thing. Those are helpful, but it's not like that is the only way to become a good physicist or a good scientist. I think we should underplay that more, so that many people think it is the end of the world if they don't get into an IIT,
Right.
or get into this medical college or that. That's a very harmful notion.
Yeah, that flexing part, people flex, okay, he's from certain college, and he
Yeah.
done really great.
Yeah.
But we have many examples who have done great despite of their college and degree.
Exactly. And so these are not how we should be. I mean, I think as humans, we don't realize that intelligence has many dimensions. And if you just kind of reduce it to one dimension, then you're not really doing justice to the multidimensional nature of intelligence. Intelligence, then not only intelligence, then other things like resilience, stamina, curiosity, imagination. I mean, there are so many dimensions.
And talking about you, what kind of intellectual environment you have grown into, talking about that early days of Bengal and then IIT Kanpur. So tell us about your environment that you saw while growing up.
So I think I was quite fortunate that I had, my parents encouraged my interest in reading books, not just science books, but all kinds of books. I used to read voraciously, and they encouraged that. So, and there were libraries which I could go to and read books from in the places I studied when I lived in my childhood. Then I had some good friends with whom later I shared a lot of interests in, say, mathematical puzzles or physics and ideas of physics. So we used to chat a lot about that, and that, it's the same thing like we were discussing about this. You talk to people, your own ideas become more real to you. Rather than sitting by yourself, and you learn new things, you learn about new books, you learn about new ideas. So throughout, whether in school or later in IIT Kanpur, I think I was fortunate to have some brilliant friends and classmates with whom I'm still in touch, and who helped me learn so much as well. And then I can never forget all the teachers in IIT Kanpur who I think really devoted their life in was not just the teaching classes, which many of them taught very beautifully, but also outside the class, in sitting in the Western labs and having chai and so on. So it was a different kind of atmosphere at that time, which it was very thrilling.
So I have heard a couple of stories about you from your days at IIT Kanpur that you with other guys used to discuss about these random questions about universe and all in what we call bulla sessions. So what were the early questions about nature, universe or physics you used to think about in your early days, during your UG days at IIT Kanpur?
Yeah, we used to. I mean, I think those are very special days when you're with other young people and you feel. I think IIT Kanpur had a way of making you feel free to think. I mean, you didn't have anything other than in the campus, so you had only these friends in your hostel, and you had these bulla sessions. So you could, and also we used to go for these long walks. At the time, the campus had a lot of open spaces, or outside near the Ganga Canal and everything. And in all these walks and other things, you could talk about the universe, the laws of physics, what does it mean, why is it that we are able to understand the universe, why is it that mathematics plays such an important role in understanding the universe, and what is the nature of mathematical truth, mathematical beauty, all these big questions. I think we used to kind of fearlessly explore, and that had its charm and its kind of formative effect on me.
So, like, I was seeing your journey and like your physics journey. So I saw like your department was physics and everyone call you physicist. But you have done some incredible great things in mathematics too. And I don't know if there is a very thin line between physics and mathematics. So if you could if you could just explain me, okay, what is physics and what is the difference between mathematics and physics and how mathematics support physics?
Yeah, no, I've always been fascinated by both subjects, and I think my first choice was 5-year program in physics at IIT Kanpur. My second choice would have been 5-year program in mathematics at Kanpur.
But you rank one, definitely you're going to get to physics at IIT.
But still, I mean, this is would have been my way of trying to distinguish the subjects, and I took a lot of subjects in some courses in mathematics also. So I had always a fascination for both subjects. I still do, and I think that kind of physics and mathematics are very closely intertwined. As you know, Newton invented calculus in some sense to understand the laws of physics and the law of gravitation and so on. So mathematics and physics have grown side by side in many ways. Of course, there are areas of mathematics which may not have immediate connection with physics, but there are areas of physics which are not very mathematical also, but nevertheless very important. So there is that, but there's a large kind of area of overlap. And the language of mathematics, as a very famous physicist once said, is unreasonably effective in physics. Unreasonably effective. So it is something which is surprising, that how very deep and maybe at first sight even quite abstract theories of mathematics turn out to be relevant in describing the physical universe. This is one of the things that fascinates me in general about physics and mathematics, and I was mentioning these conversations earlier about that. But the area that I work in is particularly one which has a much stronger mathematical component than many other areas of theoretical physics even. And in fact, some of the ideas from string theory have helped to produce new mathematics. So it's quite remarkable that from purely physical intuition or physical reasons why some things must be related, you see that things that are mathematically very different get connected. And this is very surprising for mathematicians. And they don't often understand the techniques by which the physicists have arrived at this, but they can see the results are true. And so that fascinates them. They work on it. So there's a very fruitful area. In fact, it's now called physical mathematics, which are a lot of mathematical areas which have grown from ideas from physics, and where mathematicians, of course, have very stringent standards for proof and rigor. Physicists are often a little more kind of fast and loose. So the mathematicians try to understand these understand some of these ideas, which they can see are true and can verify in many cases. Then they try to understand it within their own mathematical framework. So I think there has been a very fruitful interaction, especially in the last maybe 4 decades between ideas in formal theory, as it is called, a lot of it from string theory and related areas, and certain areas of mathematics. And it's a source of fascination. So it is something that I have also participated in, and so I feel it's very thrilling.
Yes, have you heard that meme, like, physicists are delusional? So, like, so just a meme. So, like, looking at your journey and the work that you did at Harvard, so I didn't had any idea that you are the Gopakumar Vafa variant and duality. So, if you could explain, like, a little bit about that work and why is it very relevant? And I think that was very relevant for mathematicians too. So, if you could just, like, tell us about that.
It's a small illustration of the kind of things I was mentioning earlier.
Right.
That sometimes physicists realize that there is a certain relation between two different topics or two different approaches, and that turns out to be mathematically very surprising. So this work you mentioned, we were inspired by some of the physics work which relates quantum field theories, which is the framework that kind of grows quantum mechanics into the most complete form for describing the forces of nature, like electromagnetism or the strong interactions or the weak interactions. And these quantum field theories are very powerful framework, which is all experimentally been confirmed. It is something that condensed matter physicists use. It is a language now of a lot of theoretical physics. And on the other hand, there are theories of gravity, which stands apart a little from these other three forces. And string theory is one such theory of gravity, which extends Einstein's theory of gravity.
Right.
And one of the discoveries that an Argentinian physicist, Juan Maldacena, one of the world's most brilliant theoretical physicists now, he described a relation between such gravity theories or string theories and certain kinds of these quantum field theories, very much like generalizations of electromagnetism or quantum electrodynamics. And that was very surprising, and it continues even now to be one of the very fruitful areas of development in string theory, because it connects gravity with many of the other forces in a very surprising way. And it is something I have been working on for the last 20-30 years as well. And but that early work in 1998, which I did with Cumrun Vafa, was about a simple example where we could see this connection work. It's a very simple version of string theory, a simple quantum field theory. And the remarkable thing is that because they are simple, they can be exactly solved in some ways. And in the process of exactly solving the string theory, we did it in a particular way which actually predicted certain integer numbers for things that mathematicians have studied. So this particular simple topological string theory, as it is called, is something used by mathematicians to study geometric properties of some spaces. And the way they studied it was in a particular way, but we had a different way of looking at it, and in terms of certain integers, and those invariants were very new for the mathematicians. And but at the same time, that was just a part of what we were doing. We were connecting that string theory with a quantum field theory, and a simple quantum field theory again, which had been solved earlier. And the relationship between these two was very unexpected, both from a physics point of view and a maths point of view. I mean, from the physics point of view, it was a kind of a special case of the more general relation that I mentioned earlier between gauge theories and string theories. Mm-hmm. But from a mathematics point of view, it was again very surprising, and that I think was why there was, and there continues to be interest in that. In fact, it's quite funny because I think those integer numbers that we defined, it still hasn't, I think mathematicians have still not gotten to the bottom of why it works. So it's still a big puzzle even after nearly 30 years. So it's a case where, physicists came up with something based on physics arguments, and which is clearly working, but is still kind of a puzzle for many mathematicians.
Wow. So I have a couple of more questions, but before that, I want to know, you are in US, you're collaborating with minds like David Gross, Cumrun Vafa, and when you came back to India. So how was the research ecosystem like? Were you missed those discussions with those legendary global physicists, and what was the difference that you saw in India?
So firstly, I came back to Harish Chandra Research Institute in Allahabad, which had at that time Professor Ashok Sen, who, as you know, is one of the legendary string theorists himself, was one of the people who had developed many of the revolutionary ideas that had been, at that time when I came in 2000, where these ideas and many new ideas in string theory had been developed, a lot of it thanks to him. So having him as a colleague was as good as having David Gross or Cumrun Vafa or anyone as a colleague. So I didn't have that this thing. And there were some other very good physicists as well at HRI. And at the same time, it was also good, I felt, that I had the space to think for myself, my own scientific agenda, and my own. It was a way in which I could bring together different strands of my thinking together in a way and develop that without, sometimes you have to be also a little away from the collaboration. Collaboration is good sometimes, but sometimes you also need to step out of it and be yourself and think a little, what is it? How do you think about it? And so that, I think those years in Allahabad helped me very much, thanks to the river Ganga. I think sitting by the Ganga was one of the most wonderful things there. So I think we used to say the HRI was like a little ashram on the banks of the river. So it gave a certain, I think, allowed me to go deep without losing the contact with people, because there were colleagues like Ashok Sen and others, and of course, I was traveling, I was going and meeting people in meetings, and other groups in TIFR Mumbai and other places in India, which also are very good scientists, very good physicists. So I used to be in touch. It was not like I was completely cut off or anything, so I was that good mixture, I think. You have to find the right balance at different stages. So the US years were good as a training, and allowed me to understand many things, develop myself as a researcher. And then, of course, you have to set out on your own journey at some point. So that's what I think the years in Allahabad helped me to.
Yeah, so I have one more personal question. Like, at any point in your time, have you ever felt that imposter syndrome? Like, okay, I am at the wrong place, or like, there are many great people around me. Have you ever felt like that even in younger days or at any point of time?
Yeah, I think you always feel that, and especially I think, in theoretical physics or mathematics, you're faced with these brilliant ideas, brilliant results, and things that people have found. You read these textbooks, you read about Feynman or Einstein or whatever, all the great these things, and then you see also. So you always feel sometimes the feeling of inadequacy. Oh, do I have something at least of what it takes to do some important, some kind of science which is lasting, and so you feel that you feel that as an undergraduate, as a graduate student, and especially in a place like Princeton, there's so many brilliant minds and classmates. As Juan Maldacena was my classmate, and so you saw all of these brilliant people, and so that self-doubt, these things are, I think, part of the natural evolution of every scientist, and but gradually it sort of falls away at some level because you feel, you're doing it also, and if you make some progress and you're doing it, you realize, yes, science has a place for everyone. Everyone can make their contributions,
Right.
however humble, however this thing.
Yeah, I think science makes everyone humble.
Yeah, I think so. I think there is a quote by a writer, and Australian writer I like to quote. He was talking about writing. He was saying, to be a writer is a journey in humility. It is to be defeated by greater and greater things. So I think, to be a scientist is also a journey in humility. It is to be defeated by greater and greater things. So you're defeated by bigger things, bigger ideas, and that's okay. There is a grandeur in being defeated by great things.
Yeah. So one more thing, like, this is personally I felt. So when I read about string theory and quantum mechanics, since I hosted a couple of scientists now, including you, so what I've realized is, like, our brains are wired, like, to understand classical physics better, to visualize those motions and everything. On the other hand, like, theoretical physics, talking about string theory and mathematics, these are not very intuitive. So, like, how to rewire that brain to visualize and understand things better.
Yeah, it's a good question. It's not very easy. And I think mathematics is, again, coming back to mathematics, gives you a certain language to do that. It's a non-verbal language, but I think you, again, once you've developed it, like in any other language, you develop a certain fluency with it, an ability to express things in that way and start thinking in that way. Just the way language shapes our thinking and our mental images, you develop a certain mental images for the mathematics that describes some of these advanced concepts. Even quantum mechanics is very unintuitive classically, like you said. So, but you develop a certain mental pictures which correspond to the mathematics, and you see the connections between them, and so I think it is a cultivated thing. Like with language, I mean, we take language for granted, but language allows us to also think about many abstract things. Precisely the power of language is that we are able to imagine mental concepts, which are not just, language does not only describe physical things, right? You say, oh, someone is brilliant, or someone is very imaginative, or someone is very compassionate, or something like that. These are abstract concepts, right? I mean, they are not, we take it for granted, but these are often things we are talking about, some states of mind which we don't think about very much. So language is full of abstract concepts, but which we have also internalized and formed mental images. So I think mathematics enables you is a different language which enables you to think in that direction.
And, like, how do you visualize, for me, imagining beyond 3D is, like, impossible. And when we talk about string theory and quantum mechanics, I think some 10 dimensions people are like, so mathematics, you purely rely on mathematical equations, or you visualize certain stuff.
You visualize at some level. I mean, you think of higher dimensional things as you often caricature them by your three-dimensional intuition, which can be sometimes misleading. 2 or 3-dimensional intuition, it can be misleading sometimes, but in some ways it can also give you a rough picture, and especially if you enhance it with mathematics, just like you can think of a 3D object in terms of its projections on a two-dimensional plane, but you need a lot of different projections to be able to visualize. I think you might have done this TA01 course.
Yes,
I
yes, yes,
Kanpur.
right,
They
right.
used to have to capture the 3D on
3D view, right.
3D view on the 2D paper, right? So it's a bit like that. You have to try to visualize through the different projections, and
So, like, for a non-physicist like me, and I want to appreciate these ideas and understand these stuff. So, I would love to, like, understand few things from you. Like, if you can explain me these things on board,
sure.
maybe. So, I think we should do that.
Great.
So, I think we should go to your office and we'll have a couple of questions there.
you.
So, since we're discussing, like, if you can explain me some of these ideas. So I'd be really grateful to have a lecture from you. I think it's a privilege to have a private lecture.
So I'll tell you something which maybe actually for everyone, something they don't realize that what string theory actually often does, because people talk about string theory in the context black holes, early universe, Big Bang. Okay, it does many things about that. But it also tells about something, gives a new angle about some things which are not are things that maybe you have been exposed to a little bit more. So you may have all studied in school. People might have talked about having a magnet,
Right.
And a magnet, and they put all these iron filings, and then these iron filings, they kind of form these patterns like this, right? You say that some, and this is actually also the pattern that the lines of force, they are called in school textbooks also, say between, say, a plus charge and a minus charge also, people draw these lines of force. Or if you put a magnet like this with a north pole and a south pole, and you put a lot of iron, you can actually see this. You just take a magnet under a piece of paper and sprinkle some iron powder, it will iron filings,
Form these circular
these kind of
structures.
things like this, right? It just keeps going like this. So so this is a manifestation of what is called the field, the electric field, the magnetic field, which is, of course, the basis of understanding how all electrical machinery, electricity, everything works, is based on the discovery of this electromagnetic field by Faraday and Maxwell and all these people. So this people understood, they wrote down equations, Maxwell's equations, for understanding how these fields change. Suppose I move these charges or move the magnet, how will this change the pattern, the geometry? So that was a very powerful concept. Now, there are other forces in nature, not just electromagnetism. For instance, in the nucleus, inside a nucleus of an atom, let's say a proton, but there are particles called quarks. So these are particles that are more difficult to see, but they have a force between each other, which is called the strong force. And that is what keeps the nucleus together. Because nucleus is made of many protons and neutrons. Protons all have positive charge. If it was only electromagnetism, they would have repelled each other. So there's a much stronger force than electromagnetism, which keeps them all together, the quarks together. What is that force? And understanding that force was a big project in the 20th century. And so you, just like a plus and minus charge, you can have a quark and what is called an anti-quark.
Okay.
So these are like you can think of as an electron and a positron, or some things like that, proton and with opposite charges, some two particles are there. Now these have a much stronger force, as I said, than electromagnetism. In fact, they have a very unusual force. In electromagnetism, as I take the charges away, like in my earlier picture, it becomes less and less attractive. When I bring them closer, they start repelling more, right? I bring two magnetic poles next to each other, you can feel the repulsion, no? If I bring two north poles together. So electromagnetism has this property that as I bring things closer, they start repelling. Whereas in the quarks, it is the other way around. When I pull them apart, they start becoming force increases. So it's a bit like in a rubber band. In a rubber band, if you pull it, the force, as you pull it, it becomes harder and harder to pull it further. No? So people pictured, and this is the correct picture now we understand in many ways, it is like in electromagnetism, but what happens is that these lines of flux are now not spreading out. They get bunched into a tube between them. So it's like a rubber band or a piece of rubber, elastic. And this is like a string, an elastic string, and its vibrations of the string. So this string is really like a physical string in the strong interactions. So unlike in electromagnetism, where it was all spreading out, which is related to the fact that the force becomes weaker, this is one where the force is stronger, and that's where it shows a string-like behavior. So the strings arise very naturally in understanding even the strong interactions and the excitations. There's like so once I imagine this as a string, I can think of, I just think of one fat string between them, and this can oscillate in various ways, and its various vibrations create new particles. And so that's the underlying idea in string theory, and you see many of these new particles in nuclear physics. And so it's not that far. The idea of a string is actually there in many systems, which are just requires a little more imagination than what we know in electromagnetism to picture where these strings can arise. It has to do in the strong interactions is the place where you start seeing them. But similar string-like objects exist in also even in superconductors and many other places. So it's not such a big leap to think of the string theories and about their ability to describe gravity. Right. Now, of course, I can go more, but I think just to give a picture of where...
So if we talk about the beginning of string theory, I think it started in early 1960s or something.
Correct.
So it initially started to study these, I think...
strong interactions and so on, exactly. And they had some success, and now we actually understand why they could not fully succeed in understanding at that time. Because these strings, if you ask what are the equations of the string, it is more complicated than what people thought at that time. And that is where the connection to gravity arises. That this string is actually now, and this will be maybe stretching your imagination more, is this string is like a shadow of a thin string which is stretching into an extra dimension. Like you can see, supposing I had one thin string here and I put a light on the blackboard, if the shadow will look thick. And so the real string, which is in this stretching out of the blackboard, that the equations of that are easier to understand than of the shadow. So that's why people in the early days, when they tried to understand the strong interactions through the string-like things, they didn't succeed very well. But what we have learned, as I mentioned earlier, about this connection between gauge theories and string theories, I was essentially talking about this kind of connection.
So we have like a lot of string-like things in nature. So it could be theory of everything, as people say.
At least a theory of some things.
Okay. So we'll talk more about this. I think we should just sit down and we'll discuss more on this. So like, as you were discussing, like, at most fundamental levels are made of tiny strings, but all the experiments that you have conducted in the past, like, seems to detect particles. And that's why many people criticize string theory. So what would you like to say to them?
Yeah, I think some of the criticism is a little premature. Firstly, like I was trying to explain on the blackboard, even in nuclear physics, you see many particles. Particles and strings are not in contradiction with each other. What seems like a particle can be an excitation of a string. And in fact, that's how in string theory we think of many of the particles. So these string-like excitations in the strong interactions capture to some good extent the kind of particles that we see in the nuclear force, so-called mesons. There are if you actually have a very simple model of the string, it explains many properties of those mesons. So so that is a signature. I think that the strings and the particles, they are not in tension with each other, so to say. So I think, at least that's why I'm wanted to say that theory of some things, I think we can understand at least the theory of strongly interacting systems through a string-like description. And because it also at the same time has a description in terms of gravity and has shown that you can capture many subtle aspects of quantum gravity like those of black holes, I think that makes it much more compelling to me that the same thing can actually is so versatile. It can not only maybe capture about things that are experimentally verifiable. If we understand the string theory of the strong interactions, which admittedly we don't at the moment, so I should say that we don't fully understand the string theory behind the strong interactions, but we can, if we do, and we may not be so far from that, that will actually, in fact, experimentally test many things in the strong interactions which we currently find very difficult to calculate. The string picture can actually tell us. Similarly, and once you understand that, it may actually come up in others, many strongly interacting theories, maybe in condensed matter physics, etc. So even if you discount the idea of string theory as a theory of quantum gravity, it can have measurable consequences potentially in other places. And the history of science is full of all these interesting twists and turns where the experimental verification comes from a very different direction from where you thought it should come or it might come. So people, of course, hope that you can still see experimental signatures in cosmology for the early universe. That may be another way in which you can see signatures of the string theory. You may perhaps see things in particle accelerators. So there are multiple ways in which you can potentially see it. String theory is talking about, when it talks about quantum gravity, it is talking about a regime which is unfortunately very hard to access. It is experimentally very difficult to access that. So it's a little glib to talk about, I think, the experimental confirmation about when we are talking about phenomena that are very special, very rare. It has happened in the beginning of the universe, or it happened in the interior of black holes.
Right. So we have seen this with many theories, people initially used to discourage those ideas, but eventually those become the foundations of many great things which are built on that. And last year, I think the scientists who captured the image of black hole, and eventually everyone is like, okay,
this exists. I think even many people didn't believe black holes could exist. Many had similar many objections. Einstein himself thought the prediction of his theory about gravitational waves can never be measured. But 100 years later, it was measured. So even scientists might not be able to imagine the technological advances or the ingenuity of experimentalists in being able to capture to verify things. And every generation improves its technological tools, its ingenuity therefore builds on that, and that's how people discovered gravitational waves.
But somehow these critics or ideas discourage you. If we leave that quantum gravity problem, if what if this turns out to be theory of everything? So have you ever doubted yourself? And
no, as a scientist, you have to be, of course, skeptical, and I think maintain an open mind that it may or may not be experimentally verified. As I said, I think it is a theory of something at least, and when I see the kind of dualities and how they kind of incredibly match, I know that it's a theory of some things, and then those things may or may not be measurable. So I'm not discouraged. I think people kind of, there's a lot of chatter, but I think it is not...
and talking about from the normal person's perspective, so why should they care about string theory? String theory, don't have any practical application yet, while quantum mechanics have practical applications. So, but why should we care about
So
this theory?
where people might have asked or might have actually felt the same things when quantum mechanics was discovered in
Right.
1925. Why should we care about quantum mechanics? It is talking about atoms and their properties, how the radiation goes from one atomic level to another. What does this have to do for us? Mostly the Maxwell's equations are good for giving us electricity, magnetism. Newton's equations describe most of our machines and engines. Thermodynamics was developed. We have many things. In fact, around 1900, people said, "Oh, the end of physics is in sight. We have solved everything. We have understood everything, and we don't. We don't need to know anything more. We'll soon sort out some small details, and that's enough for everything, our applications, whatever." But quantum mechanics, as you said, is now the basis of so much of modern technology, our modern day life. None of these instruments, nothing would have existed without
Like even
quantum mechanics.
every talk that government is having these days is about quantum computers, everything about quantum, like quantum communication and these stuffs. And also, like ICT is also developing that quantum city around the institute.
Correct.
So if you can tell us about potential of quantum computers, and are we going in the right direction with National Quantum Mission and the quantum city that is going to be developed around the institute?
No, I think absolutely, because it's a very important mission for the country, because so many interesting technologies, developments are still coming out of quantum mechanics, because it's only maybe in the last few decades that we have achieved the ability to manipulate quantum systems at a very individual, small level. We used quantum mechanics for many. We built lasers, we built transistors, we built all the chips built on them. We had atomic clocks. All of these MRI machines, all of these used quantum mechanics. They used the principles of quantum mechanics. But now we have an even more superior way of actually creating quantum systems, design quantum systems, and manipulate them in ways which we have so much more control over them. And that is opening up many new technological applications. And I think India absolutely has to see this as a national priority, and all the efforts that are possible at the central level, state level, individual level, philanthropic level. I think people have to be very invested in this. But again, it is a question similar to what you were asking when Feynman and some others, they talked about the potential of quantum computing in, I don't know, the 70s or late 60s, 70s sometime. No, I mean, people thought it's just some fantasy. I mean, it is just, okay, you cannot build these things. It's just a theoretician's fantasy. But that is the amazing thing, that in 50 years, thanks to a lot of technological development, theoretical development, we are now at a stage where people are thinking of quantum computers in maybe 5 years or 10 years. Okay, different people have different estimates, but they're not saying 100 years. They're building small prototypes which can do small things, but they can scale up potentially. It's a big enterprise worldwide. But no one would have dreamt of this application. So this is why the pursuit of knowledge, interesting knowledge, is very important, because you cannot predict. You cannot imagine where the new technological ideas will come from. You do the same old things, you'll just do the same old things. The new things will not come out of it.
And now you're building that quantum city around the institute.
Yeah, so the state government is very interested in using the fact that ICTS is a intellectual kind of a nucleus, a quantum city which will have maybe some other institutions, maybe a lot of labs, fabrication facilities for startups to create quantum devices, quantum materials, new kinds of quantum sensors, and quantum computing components, and which will, I think, be a very exciting thing. I think and ICTS is very excited to be part of it and help in kind of
Right.
developing
And
it.
I think as you're mentioning, like, ki those quantum computer and those things were fantasy around 50, 60 years ago. And I think now questions have changed. Like, ki could it be that powerful to simulate our own universe and
Yeah,
those kind of
yeah.
stuffs.
You can ask these new questions once you. This is the thing about science. Once you understand some area, you take it to that frontier, it opens up a whole new set of questions which you
Right.
couldn't have even thought of. And so today's fantasy becomes tomorrow's reality. And it has always been the case with physics and most of the sciences. So we should not be asking too much fixated on this question, oh, will there be an application? Will there be an application? Application may not come in 5 years. Quantum computing, the people who built the superconducting quantum qubits, which are the basis for the current quantum architecture, that the mainstream quantum architecture, they got the Nobel Prize last year. There's a student, postdoc, and a faculty member. They did it for purely curiosity. They wanted to create a macroscopic system, so-called Josephson junction, which exhibits macroscopic quantum phenomena at a kind of a relatively bigger scale than atomic scale. And they succeeded in doing that. And they were not doing it to build a quantum computer. This is what I want to emphasize. They created this just so that they wanted to show that you can show quantum behavior at a much larger scale than the atomic scale. In fact, this had been predicted by a theoretical physicist, Tony Leggett, who had gotten the Nobel Prize earlier, and who got it not at that time, but so again, it was like a theoretical prediction. These people experimentally built it, and then one of them or two of them, they realized they could use this to make a quantum computer.
Right. So, like, are we as a country understanding, like, ki the journey to deep tech is through deep science? And are we
Absolutely.
investing enough? Are you seeing the changes? Like, earlier people used to go west. And so, what is the situation now in India as in our temperament and as a country?
I think there is an increasing change. I don't know how widespread it is. It's a beginning of a change, I think. Many people do appreciate the importance of deep science for deep tech or other things. But unless you have that foundation, you will be only borrowing things from elsewhere. And many people now want to build things in India. I think there is sufficient capital. I think in principle, I think India should be spending more. But at the same time, India should be training more people also. We talk about spending often, but we don't pay that much attention to training people in these sciences. So the science programs at the IITs are so small compared to the engineering.
Right.
And of course, now we have ICERTs and other places which are good, but then we have to create institutions that will absorb all the people trained in these institutions.
Right.
So we have to really broad base our science system, and not a handful of institutions. It should be very deep kind of a capability that has to be built.
Right.
So that will take time. It will take investment in both humans and institutions. And in the humans, it goes back to the point we talked earlier about curiosity.
Right.
And we need to not just any humans, we need people who have that curiosity, who can come up with new ideas here rather than just kind of improve on something that someone else has done. Why can't we do it? We do
Right.
it.
So since you are running out of time, I have a couple of, I'll take two questions more. So, like, if you're 22 today and you got offer from Princeton and ICTS-TIFR, so what you would have chosen? So looking at the,
as a PhD student,
Yeah, as a
and,
PhD
the
student.
well, I mean, I would still say you should go to Princeton, and you should experience that atmosphere and then come back to ICTS. And because you'll spend 5 years in Princeton, but you will spend 50 years in
I think
India.
that exposure is very good and very important.
Yeah.
And the last question, how do we make research mainstream, aspirational for many young grads, like corporates and civil services? So how we can make it aspirational?
I think people don't appreciate often that being in a life of science, while it has many challenges and so on, it is very fulfilling. It is very rewarding at a very deep level, because you are also free to pursue. Largely, I think you can create a domain in which you are free to think your thoughts. Once you're a faculty member, no one is going to ask you, oh, do this or study that.
Sorry to interrupt you, but I have seen the life of professors. They are very chill. They take classes. They do startups. They do research, and they live the longest.
I hope so.
Please, definitely, please continue.
No, I think there is a certain mental freedom you have, and you're not kind of someone else's wage slave, so to say, and you might be paid much more in these things, but in the end, you have to perform as per their requirements. And whereas here, you set the agenda, which is challenging, because to set the agenda and to keep up that momentum, you have to keep having the drive. You have to have the fire to keep being this thing. Otherwise, you can also settle into mediocrity and kind of chill in that way also. But you should be able to, and I think that's where the atmosphere of an institution is important, that no one feels like just kind of theek hai abhi naukri mil gaya or kuch karna nahi hai.
I think science is about that internal fire, antaragini, ki you need to do that for yourself, for passion, and we as a country should encourage science and tech, So I'm very aspirational for future of India.
And I think you're doing a great job, Rocket Media. I think that's a great thing that you're bringing this to the awareness of young people and encouraging more people into these areas and creating an awareness that these are our foundations. You need them to really become. Then you will be really a world.
I think discussions like this helps a lot. So thank you so much. Thank you so much for your time and chatting with me again. And I hope we do more episodes like this.
Sure, if there are more things, if you feel we can talk about other things, we can definitely do that.
Sure, definitely, and maybe you can give me a couple of more lectures. I think next time I'll be prepared enough to do some advanced lectures.
Okay.
So thank you so much. Thank you for your time.
Wrap up.